Hello everyone, I'm Junya. I'm a PhD student at University of Illinois Urbana-Champaign. The title of my presentation is Functional Connectivity Analysis: An Efficient Method to Model Infrastructure Functionality, and I have done this work together with Dr. Sharma and Professor Gardoni. Infrastructure functionality is essential to communities' well-being and prosperity. However, the aftermath of past disasters has shown that infrastructure are vulnerable to natural and anthropogenic hazards. Connectivity analysis and flow analysis can be used to assess infrastructure functionality after disruptive events. There are pros and cons when performing connectivity and flow analysis for the aftermath of disruptive events. Connectivity analysis analyzes the performance of damaged infrastructure through changes in the topological connectivity of the infrastructure. It demands limited data and has low computational costs because it does not require physical attributes of components and does not model the flow of resources of the damaged infrastructure. However, it only provides partial and approximate results because it fails to fully describe operational physics of the damaged infrastructure. Flow analysis offers high-fidelity results of infrastructure's abilities to withstand and recover from disruptions because it describes the physics of system operation. However, it is data and computationally intensive, considering all the physical attributes of components and detailed operating mechanisms. This work proposes a new method to achieve a trade-off between providing functionality information comparable to flow analysis and saving computational costs in modeling the functionality of damaged infrastructure. Here shows the outline of my presentation. First, I will introduce the proposed method, functional connectivity analysis, and use the potable water infrastructure as an example. Next, I will illustrate this method with a case study of the potable water infrastructure in Shelby County, along with a comparison of connectivity and flow analysis. Finally, I will conclude my presentation. This research proposes functional connectivity analysis as a way to achieve the trade-off between providing sufficient functionality information and computational efficiency. FCA in total has 5 steps. The first step is to define ordinal states of functionality to represent the consumer perspective. Step 2 is to introduce nodal weight to connectivity metric to incorporate performance-related information. Step 3 is to define a mapping from the performance-weighted connectivity metric to ordinal states of functionality. Step 4 is to use limited number of simulations to calculate weights. Finally, use weighted connectivity analysis to predict functionality. In the next few slides, I will go over the details of these 5 steps. Step 1 is to define ordinal states of functionality to represent the consumer perspective. Infrastructure performance can be measured on a continuous scale. Say performance measure Q belongs to 0 to 1. Q equals 0 defines a completely non-functional state. Q equals 1 defines a fully functional state. Q between 0 and 1 denotes some partial levels of functionality. During a post-disaster scenario, consumers care for whether the resources they obtain satisfy certain minimum requirements rather than the exact amounts. We define the performance measure of demand node I, Q sub OI, belongs to a set of Q sub M, where Q sub M are ordinal states denoting the levels of functionality. By this step, we reduce the computational cost while sufficiently encoding consumers' utility. Taking potable water infrastructure as an example, we use 3 ordinal functional states to represent the consumer perspective. When the pressure at a demand node I, P sub I, is below the minimum pressure, consumers cannot receive any water. In FCA, we use not functional to correspond to this state. When P sub I is above the required pressure, consumers can receive the desired amount of water. In FCA, we use fully functional to correspond to this state. When P sub I is between the minimum pressure and the required pressure, consumers can only receive part of the desired amount. In FCA, we use partially functional to represent. Step 2 is to introduce nodal weight to connectivity metric to incorporate performance-related information. We choose nodal efficiency as the connectivity metric and we introduce nodal weight to it. Hence, we can obtain weighted nodal efficiency for demand node I, eta sub kappa I, as 1 over the number of source nodes multiplied by the multiplication of the inverse of the shortest path between the nodes I and j and the nodal weight. For a potable water network, when calculating weighted nodal efficiency, instead of using all source nodes, we only use a subset of all the sources. Because for damaged water network, even though a demand node can be connected to a distant source, this source may not supply water to this node because of the pipe damages. Hence, we only choose a subset of all sources to match the actual functional state of node I for the damaged network. We propose to use the weighted nodal efficiency loss L sub I as the performance-weighted connectivity metric of the water network. L sub I is calculated as 1 minus the weighted nodal efficiency of demand node I of damaged water network over the weighted nodal efficiency of demand node I of the undamaged water network. Step 3 is to define a mapping from performance-weighted connectivity metric to ordinal states of functionality. Performance-weighted connectivity metric alone cannot directly predict the functional state of demand nodes. Hence, we define a surjective mapping from the metric to the ordinal states of functionality. For the water network, we propose to use the minimum pressure over the operation pressure of node I and the required pressure over the operation pressure of node I as two thresholds of the ordinal functional states of demand node I to define the mapping function M. Step 4 is to use limited number of simulations to calculate weights. In FCA, we use a limited number of simulations to estimate the supply end nodes for damaged network without performing a detailed flow analysis. We calculate nodal weight as the proportion of the supply under damaged conditions to the supply under normal operating conditions. For potable water infrastructure, one of its essential performances is whether the demand nodes are satisfied with the required pressure. Thus, nodal weight for demand node I is defined as the pressure of demand node I when there are only damage to pipes over the pressure of demand node I under normal operating conditions. We obtain this nodal weight by performing pipe damage analysis. First, we obtain the operation pressure of node I by performing the hydraulic flow analysis under normal operating conditions. Next, we obtain the P sub dgi by performing a simplified hydraulic flow analysis, referred to as pipe damage analysis of the water network. That is, we perform the hydraulic flow analysis but only consider damage to pipes, assuming other elements like pumping stations and storage tanks are undamaged. FCA supports using low temporal resolution, like daily or lower, because it is good enough for mitigation decision making. In contrast, hydraulic flow analysis requires high temporal resolution, like hourly or higher, for the convergence of the dynamic flow equations. Hence, for weight calculation in FCA, using low temporal resolution can substantially reduce the number of pipe damage analysis, thus saving huge computational costs compared with flow analysis. Once we have the nodal weight, we can calculate weighted nodal efficiency loss. Then, we can determine the functional state for each demand node I in the infrastructure network through the mapping function M. We present the proposed FCA through an example of modeling the potable water infrastructure in Shelby County, Tennessee. In the example, we consider a 7.7 magnitude scenario earthquake with the epicenter at the northwest of Shelby County. We compare the results of connectivity analysis, flow analysis, and the proposed FCA. For the first 3 days after the earthquake, almost half of the demand nodes are determined as connected by connectivity analysis, which does not match the result of demand nodes meeting the required pressure in flow analysis. This is because even if a node has a surviving path connecting to the source, Damage to other links causes a loss of resources, significantly reducing the surviving connection's functionality. In contrast, FCA provides comparable results to flow analysis, because FCA incorporates the information on the supply reductions of links into the weights for relevant demand nodes. As for CPU time, compared with flow analysis, FCA can save substantial computational costs. In general, the ratio of computational time needed per day for FCA compared to flow analysis decreases as the number of days increases. Because if we want to assess the functionality of the water network for t equals n days, FCA can be performed specifically for t equals n days only. In contrast, flow analysis needs to be performed from t equals 0 day to t equals n days continuously to obtain the results. Finally, I will draw some conclusions. This research proposed a novel functional connectivity analysis that can achieve a trade-off between providing functionality information comparable to flow analysis and saving computational costs in modeling the functionality of infrastructure subjected to hazards. By incorporating the information on the supply reductions of links into the weights for relevant demand nodes, FCA can efficiently account for network damage and connectivity metrics, and reduces computational costs by performing performance-weighted connectivity analysis rather than pure flow analysis. The proposed FCA can enable the evaluation of infrastructure functionality in probabilistic analysis and optimization applications for mitigation. That's all for this presentation. Thanks for listening, and questions are welcome.